In our last section, we looked at the idea of summing rectangles to find area. So let's go ahead and look at a quick little review about that. So the area we realized would be the limit as n approaches infinity. N is the number of rectangles of our left sum. We could get the same answer if we had an infinite number of rectangles as well with our right sum. And then we also looked at the fact that if we used a midpoint, which is m here in this particular case, I could get an even better estimate. So this was kind of a quick review of what we did before when we were summing rectangles. Now, one of the key features of this process was that the area that I was trying to sum was equal to or above the x-axis. So that was one of the important characteristics that I had here. So the integral that we'll end up talking about eventually goes from a to b, and it's a bounded area, and it's bounded above by the graph and below by the x-axis. Now, when we look at this, again, we have to assume that this is continuous. Okay, is one of the things that we have, and also that it's positive. We also looked at rectangles of equal width. So that's kind of our background that we have going into this conversation today. So again, we had rectangles that were of equal width. What we're going to look at now is the idea of Riemann sums. Now, Riemann was a mathematician, and he came up with this idea of Riemann sums, which is a more general approximation to area. We don't have to have all the constraints that we had in the previous section. So with this more general approximation to area, the rectangles do not have to be of equal width. They can be, but they don't have to be. And then also, the height of the rectangles can be any value of f of x in the subinterval. They can not just be left, middle, or right. I can choose any value. So the height of the rectangle can be any value of f of x. Meaning we don't have to use just left, right, and midpoint. For instance, if I thought a better estimate would be somewhere right in here, that's okay. I can just pick that value and find the height of the rectangle. Now, what this is getting toward is the idea of a definite integral. So I don't want to spend too much time on Riemann sums because they're going to be very similar to what we've already done with summing rectangles. But I want to kind of get into the idea of using Riemann sums to define a definite integral. One thing that we do need to talk about is the idea of signed area or net area. I'm used to the term signed area. This textbook uses net area, so these mean the same thing. So if I were to look at a graph, and some of the graph is above and some is below the x-axis, that's going to start talking about signed area. So let's say we have a graph that looks something like this. And this is going to be 0, this is going to be A, and this is going to be B. So if I look at this graph from 0 to A, the area is positive. So again, this is positive area. If I look at this graph from A to B, this area is negative. So area is negative. Now if I just assign some values here, let's say that the area up here would be something like, say, 12 square inches. And let's say the area down here would be 4 square inches. Now because it's below the x-axis, this would be a negative 4 square inches. So there's a couple things I'm looking at here. If I look at my total area, you can see that there'd be a 12 and a 4. So that would be our 16 for our total area, but our net area, which is what our integrals come up with, would be 12 minus 4 would be equal to 8 square inches. So the idea of this net area is going to be really important. And again, our total area of the regions would have been 12 plus 4 would be 16 square inches. So it's important that you know the difference between net area, because I have a positive and a negative area I have to combine, and then total area, I would be just looking at the area covered, whether it's positive or negative, and I combine those. So down here I wouldn't count this as the fact that it's below the x-axis, I just count the fact that it's area. So those are some really important ideas to keep in mind when we're working with these. Now you can look at Riemann sums in terms of everything that we've just done. You know, you can sum your rectangles and do the whole process from there if you need to. But really we want to get into the idea of a definite integral. Now there's a direct connection between Riemann sums, the summation notation that we looked at before, and a definite integral. A definite integral is basically finding area where I have limits of integration. So this means the integral from a to b of my function f of x dx, and we're going to go ahead and see the similarities between these two. This is directly related to the idea of summation notation. With summation notation, I have the limit as delta x, or delta approaches 0, number of rectangles approaches 0 if you want to think about it like that, as k goes from 1 to n, or n equals 1 to k, depending on the notation that you use, of my function times delta x. So this is called my lower limit of integration. This is called my upper limit, as you might guess. This value of f of x is called the integrand. It's the height of a rectangle. And then this value of d of x is called our differential, and it's basically the base of a rectangle. So remember what that we're getting at after here before. This integral sign means I'm summing rectangles from a to b. I'm summing their areas, and the area is found from the height times the base. And so this is that shorthand notation to represent that. We don't have to go through the process and take a limit. We can use our power rule of integration from there. Now there's a lot of different ways that we can work with integrals. We can find integrals using that power rule. We can also look at integrals using geometric shapes. Let's go ahead and set up some examples where we're finding integrals, and for our first couple problems, let's go ahead and look at some rules of integration. Now some of these we've already looked at. The integral of a sum is the sum of the integrals and some things like that. So the integral of a plus b is just equal to the integral of a plus the integral of b, and this would work with plus or minus. But remember, this doesn't work with a product, and it also doesn't work with a quotient. So remember, this only works for addition and subtraction. Now when we're working through with these problems, the only thing I can pull out front would be any coefficients. So let's look at an example, let's say like 3x squared plus x plus 2 dx. Now I want to integrate this, let's say from 2 to 5. We might get some big numbers here. So when I integrate, remember you add 1, divide by the sum. So I'm going to do that to each piece here. Now this is an implied 1, so this would be 1 plus 1 over 1 plus 1. Now this x is to the 0 power, because there is no x there. X to the 0 is 1, 1 times 2 is 2. So I'd add 1, divide by the sum. Now usually I have a plus c here to say, okay, this represents an entire family of solutions. But because I have a definite integral, I'm evaluating this at a particular point. So I don't really need to worry about that plus c. I no longer have an entire family of integrals. And I'm going to evaluate this from x equal 2 to x equal 5. So this is that notation I use. I need to simplify this. So I have 3x cubed over 3 plus x squared over 2 plus 2x over 1, or just 2x. This simplifies. The 3's cancel. And I'm left with x cubed plus x squared over 2 plus 2x. And this is evaluated from x equal 2 to x equal 5. I always take my upper minus my lower. These always need to be in parentheses because a big mistake that ends up happening is the negative sign doesn't get distributed and we have a mistake there. So again, this is always going to be my upper minus my lower. So plugging in, we get 5 to the third plus 5 squared over 2 plus 2 times 5. There's my upper. Let's go ahead and look at our lower. So for my lower, I'm going to plug in a 2. So that would be 2 to the third plus 2 squared over 2 plus 2 times 2. Now I'm not sure if this falls below the x-axis or not. I didn't graph this, so I don't know if what I'm getting is going to be net or signed area. We can always assume it's going to be net area for our solution. If I look at a picture and I see that it's all above the x-axis, the net area and total area are the same. So let's go ahead and evaluate here. So 5 cubed is 125 plus 25 halves plus 10. And then I'm going to distribute the negative as I work here. So negative 8 minus 2 squared is 4. 4 over 2 is 2, so that's minus 2. 2 times 2 is 4, so that's minus 4. So I have 125 plus 10 is 135. Actually, the plus 10 and these cancel. So 125 minus 4 would be 121 plus 25 halves, finding that common denominator. Looks like I have 242 plus 25 over 2. So it looks like 267 over 2. This would be my area. Now again, we don't know if this is above or below, so I have to just assume that it's net area once I get my solution. If we wanted to graph this, we could. In fact, let me pop open my calculator. That's going to be a whole nother problem that we're going to work with. A lot of your calculators will do some of these basic integrations so you can check your work. If we go to math, and then we're going to come down here to function integration. So that's option 9 on my calculator. If you notice, we just fill everything in here from 2 to 5. And then we put our integrand in here, so that's 3x squared plus x plus 2. And then you have to tell it with the width that we're looking at, what variable, and that's dx. So there's an example, and we get 133.5, and I think if we divided out what we got, 267 over 2, we get 133.5. So you can see that that checks. So on a test, you are allowed to use your calculators. So you can see that I'm not going to be really interested in the answer at all. I'm going to be interested in your work and how much work you show. So the more work you show, the better. The less work you show, the worst, because I know you already can find your solutions for a lot of these problems. Now let's go ahead and take this value and graph it as well. So let's graph 3x squared. I already forgot that one. 3x squared plus x plus 2. So let's go ahead and graph that. Now I'm only interested in this from 2 to 5. Oh, it's totally above the x-axis. So 2 to 5. I don't think we're going to be able to curve sketch this very well because this goes 1, 2, 3, 4, 5. We don't even know where this ends. It's going to end somewhere clear up here. We could change our window if we wanted. This might just be too big of numbers to be working with. Let me get to y max. So if we plugged in a 5 in here, we'd have 5 squared is 75, 8, let's do 100 here. Let's see what that looks like. Okay, so there we got it. So now if we look at this from 2 to 5, that's this piece right here. So let's just try something real quick. Second calc, and look at, we have an integral sign down here on option 7. And I'm basically saying I want my lower limit to be a 2 because that's for my lower limit of my integral, and my upper limit to be a 5. And what it's going to do is it's going to shade that area that I'm finding. So this is a picture of the shaded area that I'm looking for. And then you can see your integral solution is 133.5 here. So once again, you're going to have a calculator, you can use it, but I'm more interested in the work, not just the answer. So very little point is given toward the answer, all the points are given toward the work. So a quick way that you can double check your work though. Okay, so that's an idea of using our power rule, and the idea of a definite integral relates back to the idea of the area under a curve in that summation notation. Okay, so we've talked about different rules of integration already. We can have a constant that we can pull out front that we can drag along and some other things like that. But one thing we haven't done is we haven't looked at any problems where we're actually using geometry. So we want to find the area, not using Riemann sums or our power rule, because some of these we won't be able to perhaps, but using geometry. So we want to get a geometric idea of what these integrals are standing for. So let's go ahead and look at the integral for our first one from, let's pick a line. And let's go from -1 to 7. And let's look at 3x minus 9. And of course that's dx. Now a lot of times you'll see parentheses here, and I'm usually pretty big on parentheses, but it's okay not to have them in here because we can see the end of the integral is given by dx. So we could integrate this, and we could actually look at this geometrically. So let's first of all graph this. If we were to graph this, this is a line with positive slope and a y-intercept of -9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So -9, and then I'm going to rise 3, run 1. So this is kind of a quick little picture that we have here. This is just a curve sketch. And this is going to go from -1, so it's going to come down here to 7. I'm not sure where this is going to cross. I think this is probably going to cross at 3, so I probably have to be a little bit more accurate. So this will cross at 1, 2, 3, 6, 7. I might have to extend that line out a little bit. Okay, so you can see what we're looking at here. I definitely have this idea of signed area occurring. So this is this area that's going to be a positive area, and down here this area that will be a negative area. So if I wanted to look at my total area, then I have two triangles here. So I'm going to call this area 1 and area 2. So area 1 would be 1/2 base times height. So 1/2, and the base we can see goes from this value of 3, 4, 5, 6, 7. So this is 1, 2, 3, 4. And then for our height we can get by plugging in the value of 7. So if we plug into 7, 7 times 3 is 21. 21 minus 9 would be 12. So I get a 12 here. Half of 4 is 2. 2 times 12 is 24. Okay, let's go ahead and look at area 2. So again, this is looking at our shapes geometrically. This is 1/2 base times height. Now our base here would be 1, 2, 3, 4 units. And then our height we could get by plugging in -1 into this value. So 3 times -1 is -3. -3 minus 9 is -12. So this is a width of 4. This is a length of 12. This was a height of 12, I believe, and this was a width of 1, 2, 3, 4. So same problem really. So I get two areas. If I add these together, 24 plus 24 is 48. This would be the area. This would be the total area. Now what would our net area be? My net area would be A1 plus A2, But I need to think about a2. a2 is actually a negative value. So this would be 24 minus 24 would be 0. Because again, we want to think about this as below the x-axis, so I can think about that as a negative because it's below. So net area and total area are two different ideas. So you might want to keep those straight because they will make a big difference in the solutions to some of your problems. Now, two other interesting properties or characteristics that we'll want to be aware of for integration. First one would be, what happens if I reverse my limits of integration? So if I have the integral from, let's say, a to b of f of x dx, and I decide to switch up my limits of integration, instead of my lower being a, I'm going to switch these up to my lower being b. What happens is I end up just negating the value over here. So the limit from b to a of f of x dx is just going to be the negative if I switch my limits of integration. So those are the couple things I want to keep in mind. Also, the integral from a to a of f of x dx, your upper and lower are the same value, so your total area covered is 0. So your limit of integration here, or your value, would be 0. Now we'll use some of these characteristics when we're trying to look at limits of integration, but not being given a graph. So a common problem that you'll be given is you'll have certain integrals provided to you. So for instance, you might have the limit of integration from 2 to 4 of f of x dx equals 8. I have no idea what the graph looks like. Some other information that you could be given would be the integral from, let's say, 2 to 7, so same lower but different upper limit of f of x dx equals 7. So this is interesting. This covers 2 to 4 and the area is 8. This covers more along the x-axis, but the area is left. So that kind of makes me think that something is below the x-axis here. And then our last one, let's say we have the limit from 2 to 7, but not of f of x, let's say of g of x dx, and that limit is equal to 2. And then we can evaluate all sorts of interesting things. So the first one we want to look at is, let's say we're looking at the limit of integration, not from 2 to 7, but from 7 to 2 of g of x dx. Well, from the rule we just learned, we know that that's going to be the opposite of the limit of integration from 2 to 7 of g of x dx. I flip my limits of integration, so this would be a negative 2. Let's look at another example. Let's say we're looking at the limits of integration from 2 to 7 of 2 times g of x dx. Remember, if I have a constant, I can pull the constant out front. And I know that my limit of integration from 2 to 7 of g of x dx is up here at 2, so I have 2 times 2, or 4, for that limit. Let's look at the limits of integration from, well, let's do, I guess we better do an f of x here too. Let's do the limit of integration from 2 to 7. Let's do g of x minus 2 of f of x dx. So again, I'm just splitting these up. You don't have to actually split these up when you rewrite them, but just for a few of these I want to make sure that you understand what the steps are. So for this first one, from 2 to 7 of g of x, I get a 2. For my next one, I have the coefficient out front, that's a 2. And then the integral from 2 to 7 of f of x dx is 7. So I get 2 minus 14, which is negative 12. So these are some examples and some ways that we can use these integrals without even knowing the shape, if I know the values. Now, one of the more interesting questions I think that we can look at here is the integral. We have 2 to 4, and we have 4 to 7, or sorry, 2 to 4 and 2 to 7. Let's look at the integral from 4 to 7. That's not given to me directly, of f of x dx. So we're going to have to think about this one. If we think about a number line, we know we have some information about 2 to 7, and we have some information about 4 to 7. So we know the integral from 2 to 4 is 8. That's given to me. So this distance is 8, or this area is 8. And then we're also provided with 2 to 7 is 7. So what that's telling me is this distance from 4 to 7 has to be a -1 in order for this to work. So I have area above and I have some area below here in order to make this work. So this is equal to a -1. And again, you can logic your way through this if you think about the signed area, positive and negative values. So these are just some examples of some characteristics or properties of limits that I can use to actually solve limits. Now we've talked about lots of different properties of integrals already. One that we haven't really run into is absolute value. So an example of using absolute value might look something like the integral. Let's go from 1 to 4 of the absolute value of 2x minus 4 dx. The easiest way to look at this is geometrically. So if we were to graph this, we know an absolute value is kind of coming to a V, that sharp V shape. So let's go ahead and just start plotting some points and see what we can come up with in terms of what this graph could look like. If we plug in a 0, we get a -4. Absolute value of -4 is +4. So we'd go 0, 1, 2, 3, 4. So there's a point on our graph. Let's go ahead and plug in a value of 1. 2 times 1 is 2. 2 minus 4 is -2, but the absolute value of -2 is +2. Let's plug in a 2. 2 times 2 is 4. 4 minus 4 is 0. Let's plug in a 3. 2 times 3 is 6. 6 minus 4 is 2. I'm getting a pretty good idea of this sharp V that's occurring here. Now I'm only interested in this from 1 to 4. So here's 1, so this is that small area. And then I have 1, 2, 3, and then 4, of course, is somewhere up here. So I have these two different regions that I want to be looking at. So we'll call this area 1 and area 2. Well, geometrically, these are both triangles. 1/2 base times height. The base of this left-hand triangle, A1, is 1 unit. And then to figure out the height, again, I'd plug a 1 in. 2 times 1 is 2. 2 minus 4 is -2. But the absolute value of -2 is 2. So I get half of 2, or I get 1 unit here. The second region, the base is going to be 2, and the height, we need to come in over here, 1, 2, 3, 4. 2 times 4 is 8. 8 minus 4 is 4. So this is the ordered pair 4, 4. So again, 1, 2, 3, 4. 2 times 4 is 8. 8 minus 4 is 4. So I get 4 units here. So if I'm looking for the total area, because it's all above the x-axis, I can just add these together. I get a value of 5 for my integral. Okay, and that's also giving me, so again, this is adding 1 plus 4 is 5. This is giving me my total area because it's all above the x-axis. And I guess in some way it's giving me the signed area as well, because I don't have any below the x-axis, so all my areas are positive. So looking at that geometrically, it will be helpful. Well, sometimes in your homework set you'll be given a Riemann sum, and with this Riemann sum you'll be asked to translate this to a definite integral. So let's go ahead and look at a quick example here. Now I'm not going to get too hung up on where this comes from. Usually this information is provided, and then once this information is provided, then what we can do is translate this into a definite integral. So this is just an example of basically the function that we have being summed. This is the width of the rectangle, and remember those rectangles don't have to be of equal width, and this is on the interval from 7 to 13. So when I translate this to the definite integral, my limits of integration would be from 7 to 13, and it looks like to me I'm taking my function and raising it to the 8th power, so this would look like x to the 8th dx. So this translates into this definite integral. Now if I wanted to use this, I could, but the definite integral is much easier to work with. So that's how a Riemann sum would translate into a definite integral. Now sometimes you'll be asked to take an expression, a definite integral, and to work backward into the Riemann sum. So what if we had an integral, let's say from 1 to 9, of 1 over, let's go 2x dx. I can't integrate this right now using my power rule, because with my power rule I have to assume the exponent is not equal to 1. So the way that this will translate then into a Riemann sum, my limits of integration go from 1 to 9. So I'm looking at the interval from 1 to 9. And let's say I'm given, for this particular case, 20 rectangles. Now this information has to be given to you. You can't look at the definite integral and figure that out. So remember, delta x is b minus a over n. So I have 9 minus 1 over 20. So that's 8 over 20, which we reduce to 4 over 10, which reduces to 2/5. So when I'm starting to find my area then of 20 rectangles, a sub 20, I know that that base, that 2/5, is out front, and then I sum my rectangles. So this is my base, and now I have to look at my heights. So my number of rectangles, and we can use n or k for my indice, it doesn't matter. I think in your homework sets they use k, so I'll switch to k so it's a little more familiar. And then I need to plug this into this function up here. So that's 1 over 2. And then this value of x is the complicated piece. So remember, if you want to think about whether we're going to use a right endpoint, left endpoint, or midpoint, that was our last lecture that we were looking at. So you might have to go back through that lecture a little bit to pick up on some of this notation. So for this one, I'm going to use my right rectangles. So I'm going to use R here. So it matters. So right rectangles. So remember, I'm starting at a 1. Now if you remember from the last lecture, we had 1 plus, basically we wanted to look at our delta x. Our delta x is given by 2/5 because that's my increment. Now I have to start, because this is my right, I'm going to start with k minus 1 or n minus 1 if you're using our n notation. Now let's go ahead and look at what the graph of 1 over 2x looks like. Kind of comes scooping down in this direction, and let's say we're looking from 1 to 9. So this is the area that I'm looking for. And I can't draw all 20 rectangles in here, but I just want to draw a couple in just to have an idea of what's going on. So if I'm using a right hand rectangle, this would be the height. So when we look at this, we can see that we're starting with a 1, and then I have to add some sort of an increment here to get to my value that I'll actually be plugging in. Well, I know that that's going to be 2/5 because I know that my delta x is equal to 2/5. And then I can see that I'm just going to add one of those 2/5. So this is just k, not k minus 1. So that would be my right Riemann sum. Now if I wanted to plug this into a calculator, I can do that. If you don't want to do that, you can go ahead and use all of your summation notations that we learned in the shortcuts. But we should be able to plug this directly in. So I'm going to use my summation notation. I'm going to look under my math mode, and mine has summation notation, and hopefully yours does as well. If not, you can do these simply by hand as well, like we did in the last lecture. So I'm going to have a 2/5 out front. Let me clear that out and put in my 2/5 first. Okay, now I'll put in my summation. So that's number 0, or option 0 on mine. So you can use a k or an n, it doesn't matter. I'll use a k to be consistent with what you'll see in your homework sets today. My value of k is right here above the parentheses, so I'll do alpha k. K equal 1 to 20. And I have that nice fraction key, so I'm going to use that. One plus 2/5 k. And you have to be consistent about what variable you're using in a problem. It doesn't matter from problem to problem which one you use, but it does matter very much when we talk about in the same problem. I can't mix n's and k's in the same problem unless I'm just looking at a general form. So here's my summation notation. It's figuring it out right now. And I get 1.01621, and it's usually pretty specific because again we're trying to find area. So let's go ahead and take a screen snip of this and pop it into our lecture. So this would be an example how you could use a calculator to evaluate these. So the calculator shortcuts are nice to check your answers, but again, I'm not really being generous with points for just answers. It's how you show your work and how you show the process that counts for the points. Now sometimes you'll be looking at piecewise functions as well. Piecewise functions are fun to work with. So let's look at the integral from 1 to 8 of f of x dx, where f of x is defined to be a step function. So f of x is equal to 2x, which is just a line with positive slope with a y-intercept of 0. And this is defined if x is between 1 and 5. And then we have 12 minus 2x is that part of the graph if we're between 5 and 8. Now notice I just don't have an equal sign at the 5 because it's already covered over here. Well, the easiest way to set this up, well, we could do this a couple ways. We could use this geometrically, or I could set up two integrals. I'm going to look at this geometrically. So geometrically I have two lines here. This is a line with a slope of 2, y-intercept of 0. So let's go ahead and start with that idea. See if I have enough room here. Whoops. Okay, so I might have to scale this a little bit different, but we'll get it done. I'm going to kind of blow up that first quadrant. So my y-intercept is 0 here, and my slope is 2. So I'm going to rise 2, run 1. And this is true from 1 to 5. So I might have to scale this back a bit. So if I put a 1 in here, 1 times 2 is 2, so I'm at a height of 2 there, so that goes to 2. And then let's go up here to 5. 2, 3, 4, 5. If I plug a 5 in, I get a 10 back. Okay, so let's go ahead and fix this up a little bit. So that's where that graph stops. Now let's look at the other part of our graph here. This is a line with a y-intercept of 12, so 10, 11, 12. And then it has a slope of a negative 2. So I don't want to start here though, because I'm kind of running across my red line, the 2x line. So I need to come out here, 6, 7, and 8. So if I plug a 5 in here, you can see that 12 minus 2 times 5, 2 times 5 is 10, 12 minus 10 is 2. So if I plug in a 5, I get a 2 back out, but it's a hollow point because I don't have equality at x. Let's go ahead and plug in an 8 next. 2 times 8 is 16, 12 minus 16 is negative 4. So this is going to go down here to negative 4. And I guess I should have started my graph on the next page. So let's pull this down, leave plenty of room. So then I'm down here. Again, if I plug in an 8, 8 times 2 is 16, 12 minus 16 is negative 4. And that is a filled point. I'm not exactly sure where that's going to cross. Let's go look at that function again to see if it crosses at 6. 12, yeah, it does cross at 6, so it does cross at this point as well. So I'm trying to find the integral. I'm trying to find this bounded area. This is not an easy question. I don't have nice little shapes running around here, except I do have a nice triangle here and another nice triangle right here. So that's good. Now up here, I'm not exactly sure what's going on, so we'll have to take a look at that. So I think we're going to call these three different regions. So I'll drop this down to my x-axis, and I'll call this region 1 or area 1. We'll use A1. And then we'll have A2 and A3. A couple things I'd like you to look at. A1 is positive, A2 is positive, A3 is negative. So we need to remember to take that into account. So A1, this is a trapezoid. The formula for the area of a trapezoid is 1/2 the height times the sum of the bases. So A1 is 1/2 the height. The height is given right here because this is a trapezoid on its side. It's a right trapezoid. So the height here is 1, 2, 3, 4 times the sum of the bases. So this base is 2 units. This base is 10 units. So I get 1/2 of 4 is 2. 2 plus 10 is 12. 12 times 2 is 24 square units for A1. So this is 24 square units. And it's positive because it's all above the x-axis. Let's go ahead and look at A2. This is a triangle, 1/2 base times height. Base here is going to be 1 unit. Height here is 2 units. It's not to scale. 1/2 of 2 is 1. And this is positive area as well. So this is 1 unit. A3, 1/2 base times height. It's another triangle. The base here is 2 units. The height is 4 units. And if you want to plug a -4 in there, you can. 1/2 of 2 is 1. 1 times 4 is 4, but it's below the x-axis, so we know it's a negative value. So it's a -4. If you wanted to plug a -4 in here, you could, or just realize it's below the x-axis to find that signed area. So the integral from 1 to 8 of f of x dx is going to equal 24 plus 1 minus 4. So 25 minus 4 is 21 units squared. Because remember, this is area. So keep in mind that signed area. It does make a difference here with what we're looking at. Sometimes when we're working with these, we're going to be given variables and asked to solve for the variable in terms of the integral. So let's go ahead and look at an example that you might see. So for instance, we're given that c is between 0 and d. So this notation means between. C is between 0 and d. Then find b, for which this statement is true. The integral from c to d of x plus b dx equals 0. So they're telling me my answer here is 0. They want me to find the value of b that makes this true. So let's start integrating. If we integrate this, we get x squared over 2. If we integrate b, that's the same as bx to the 0. I add 1, divide by the sum, and I get bx. This is evaluated from c to d. So I plug in a d. I always go my upper minus my lower, and I'm going to get 0 for my answer here and then solve backward. So plugging in a d, I get d squared over 2 plus bd, because I'm plugging in, if I should clarify that, x equals c and x equal d. I know that because my dx tells me my variables that I'm subbing in for, so x equals c, x equal d. And then I plug in for c, so I get c squared over 2 plus, and then I plug c in for x and I get bc. Okay, so let's go ahead and simplify this. I get d squared over 2 plus bd minus c squared over 2 minus bc. The negative distributes and I get equal to 0. Now what I'm asked to do here is to solve for b. So again, my directions, find b. So I want all my b's on one side, everything else on the other. So I have bd minus bc equals c squared over 2 minus d squared over 2. I can factor out a b on the left. And I'm left with b times the quantity d minus c. And I have a common denominator here, so let's go ahead and combine those. I'll finish this off by dividing through by d minus c. And I get b is equal to c squared minus d squared. Oh, that's a difference of perfect squares. Let's rewrite that. C plus d, c minus d, all over 2 times d minus c. Now if you notice, these are really, really close to canceling, but not quite. So let's go ahead and rewrite this, and then let's factor a negative. Well, I could factor a negative out here or the denominator, it doesn't matter. So I'm going to pull a negative out front. If I factor a negative away from a negative c, I'm left with a positive c. If I factor a negative away from a positive d, I'm left with a negative d. And you can see that these cancel now. And I'm left with b equal negative quantity c plus d over 2. I pop the negative up top. Now this could also be distributed. The negative could be distributed as well for an equivalent solution. So there we're using a lot of algebra and the concept of a definite integral to help us work there. As usual, if you have questions, please let me know. You can send me a screenshot. We can also jump on to some online office hours if you can let me know when you're available. We also have Pearson Connect. If you have any questions, make sure you let me know. Good luck.